So a function, we've already dealt with functions here. We've dealt with linear functions, which when you graph a linear function, what does a linear function look like? A line. That's why they call it linear function. That's when, y equals mx plus b, slope intercept form. But we've also dealt with quadratic functions. We actually dealt with it before the break, and then we've been working again with quadratic functions. So you took a test on. What does a quadratic function look like? A parabola. Okay. Well, now we're going to deal with exponential functions, but understand when you use the word function, a function is an equation that has an x and a y, an input and an output. Here's your equal sign for the equation, here's your y. But the reason why they call it exponential is because now the input, the x, is going to be the exponent. Again, you dealt with equations before where the x was the base, and on a linear function, what's the exponent? What's the exponent of the x? What's on top of the x? A 1. On a quadratic function, that looks like a parabola. Again, the x is not the exponent, the x is the base, but what's the exponent? A 2. Well, first of all, now what happens is that these two flip-flop. Now the base is not going to be the variable. The base is going to be a constant. And what makes this, I don't know, like a little bit confusing is that, unlike with these, like it's not like we're going to just be working with one constant at a time. That base can be any number. It could be, 2 to the x power, 3 to the x power. It could be a fraction to the x power. So the base can be any number, but now the x, the variable, that becomes the exponent. So the way we approach these is we have a basic understanding of what this looks like. How depending on the base, if all we were to change it, if the only thing we had was a base and then the variables, what that would look like, what basic shape that would take. Again, we just talked about the basic shapes of these. What does a linear function look like? A straight line. Okay. What does a quadratic function look like? A parabola, a U. Okay. Well, exponential functions can look one of two ways. There's two possible ways it could look. But then once we figure out what is that kind of starting look, the way it looks before anything happens, then we're going to discuss transformations. Okay. Even though we didn't discuss transformation with lines. Okay, lines can be flipped. That's why you learn about negative slopes. Parabolas can be flipped and slid and stretched. Well, the same thing with exponential functions. But first, we learn what it looks like just basically, what we call the parent function, what it looks like, and then we can talk about transforming them. It'll be the same 3 transformations you learned before. What are those transformations? What are the 3 basic? There's really 4, but the materials I have only have 3 of them. Stretch and compress, and that's still going to be controlled by the same value, which was, hold on, what controls stretches and compresses? A. Okay, what else? Reflection, which are also controlled by A. You're going to see an A here. You just got to know where to identify it and where it's going to be placed. And then translations. What number controls horizontal translations? Horizontal is this horizon. H, good. And then what controls vertical? Okay, so you'll see the same things. It's just that now instead of starting with a U, with a parabola, we're going to start with exponential functions, which again can look one of 2 ways. It depends on the base. So let's talk about the transformations first. Okay. The reason for this is so that you know where to find A, H, and K. I want you to compare and contrast. Compared to what I just finished talking to you about, what do we still see? We still see a y equals. We still see an x. Actually, let me do this way. We still see a base with the x. We still see a base with the x. But now you see the 3 other values. If there is an A, A is going to go in front of the base. Sometimes people get the base confused with the A because since the base isn't, it looks like the base is in front of the X, they think the base is A. No, A would have to be in front being multiplied. If there is an H, it's going to be up there on the exponent with the X being added or subtracted. Be a little number, right next to the X. Just like before, notice how the H has a negative in front. So whatever H you think you're seeing, H is actually the opposite sign. You got to change the sign. And then K, just like before, is being added and subtracted on the outside. And they're still in charge of the same thing. Okay. Hold on to this formula. I had introduced this to some of my kids when we were doing parabolas. But then we kind of learned the more watered down version of doing parabolas where we counted from the vertex. I don't know of any other way to do exponential, so you might want to highlight this. This is how we're going to perform the transformations, but we have to actually graph. Unless somebody, unless I somehow come across a way that's more simple. I don't think this is too challenging, and actually this would be, erase this. This should just be an X. So we don't get into C. Take off that divided by C part. That's my fault. I forgot to take that off. C is another transformation that we don't have to worry about. So just put, so it'll say X plus H comma Y times A plus K. On your paper, James, I forgot to erase. This is on the book I got this from. They had another transformation value called C, but just put that as X plus H. Take the C off. All right. So what are those two basic shapes that an exponential function could take? Well, one is called a growth and one is called a decay. Assuming that A is greater than 0, what numbers are greater than 0? What numbers are greater than 0? What group of numbers are greater than 0? Positives. So what this is telling you is assuming that A is positive, because what did we learn happens when A is negative? What did we already learn with parabolas happens when A is negative? A reflection. So we're just saying, hey, assuming that no reflection has occurred, okay, assuming that A is some type of a positive number, if the base, so the number underneath the exponent, if the base is greater than 1, that's called an exponential growth. If the base is between 0 and 1, what types of numbers go between 0 and 1? Proper fractions. Any fraction where the numerator is less than the denominator. Then you have an exponential decay. Now the smart person in here might say, but hey, Mr. Romero, how, that we're still missing a big chunk of numbers here. You talked about what happens when the base is greater than 1. Well, you talk about when the base is between 0 and 1. What happens if the base is negative? Base can't be negative. It would cause what I call discontinuity in the graph. The graph wouldn't be continuous. It would jump around. So you are not going to see any bases that are negative. If you do see a negative underneath the exponent, you won't see a parentheses, which really means that the negative is A. It's not the base. The base would just be the cross that bridge, we'll get there. I'm not trying to. So anyways, this is what it looks like. These are the basic shapes of a growth. Okay, so on the left, the way a growth looks like. Now I know it looks like it stops here at the y-axis, but it doesn't. It keeps on going. Okay, a growth as you go to the right, you also start to increase. It looks like that. That's the basic shape it would take, and it goes on forever up. It does not go on forever down. We're We're going to talk about that in a second. But a growth does go forever up. A decay starts, if you're going from left to right, it starts going up. And this actually also does go forever up. As you go to the left, you go forever up. But then it starts to go down. But as it's going down, it starts to kind of slow down and level off, level off, level off. This, just like a growth, will not go forever down. Those are the basics. Before you start flipping them and stretching them and sliding them, this is the way it looks at the beginning. If I ask you what does a growth look like, you would draw something that looks like this. If I ask you what a decay looks like, you would draw something that looks like that. That's like the basic shape. Now, the reason why these do not go on forever is because they both contain something called this is going to be one of your fun math words. This and hypotenuse are two of my favorite math words. This has what's called a horizontal asymptote. Oh, there's another word called apothem. That's another fun math word. You might get to that in geometry. Apothem. Apothem, hypotenuse, and asymptote. Say that 10 times fast. What an asymptote is think of like a force field. Think of like an invisible force field. It's an invisible line that your graph gets close to, but it'll never touch. And it keeps on going forever and ever and ever and ever and ever and ever, but it will never reach there. Exponential functions all have a horizontal asymptote. Horizontal asymptotes are located at the horizontal line, y equals k. Whatever k is, you draw a horizontal line there, and your exponential function will either have to be above, or if it flipped, because a is negative, it'll be below. But you can't cross a horizontal asymptote. At least not an exponential function. By the way, if you're freaking out, don't freak out. We have 2 days to cover this. The packet I just gave you, we have today and tomorrow. So we're going to go nice and slow. 2 days. Just don't tune me out. If you tune me out, then caca for you. And then Friday, I bring the lab cards in again. Before we get to examples, one little piece. You're going to be asked about end behavior. You should have heard that word before. It might have. We talked about it before a little bit. Behavior, don't think of behavior like conduct, like oh, you have good behavior or bad behavior. Just think of behavior as what's going on, like what's being done. What happens at the ends of graphs? At the physical ends of graphs, what do you see at the ends of graphs? Arrows. And what do arrows mean? Huh? An arrow means that something goes on infinite, right? So when you talk about end behavior, you're being asked what are the arrows doing? So here's how they're going to show end behavior in what's called arrow notation. Okay? You're going to need to know this if you ever decide to take a calculus course and you learn about limits. You need to know arrow notation. So this is conditional. Okay? There's conditions. So first off, what you're seeing here on the left, this goes with the growth. Look at the condition, the first condition. As x, the arrow means approaches. You can write that down. You see an arrow. That arrow in words means approaches. Sorry for my handwriting. And you want to help out with the Vietnamese translation of approaches? You don't know the translation? Should I use Google Translate? Let me see if I can use Google Translate. And I never get a chance to use it. And then you tell me if it makes sense. Does that make any sense? It does? Approaches? Okay, that's what the arrow means. Approaches. Her Vietnamese is stronger than yours? So remember, think of this as if, right? There's like an if x is going to negative infinity. What direction are you going if x is going to negative infinity? Left. So this is just a way of asking you, hey, on a growth, what is the left arrow doing? Where is it headed towards? I know we're going left, but as far as up and down, where is it going? Huh? It actually isn't. Now it is going down, but because we have a horizontal asymptote, it's never going to reach the horizontal asymptote. Huh? Okay. As x goes to negative infinity, x going to negative infinity is left. So this is asking you, hey, what is the left arrow doing? The next part I'm going to reveal is then what the y is doing. So x is going left. What is the y doing? It's going down. The part that I corrected you on is you said negative infinity. It actually is not going all the way down to negative infinity. Well, yeah, yes, x is going to negative infinity, but the y is going to go down to the asymptote, which is going to be the k. Now, you don't have to really worry about it for now, but just in case if later on, if you see this, like we're going to say like k plus, that's saying that it's going towards, look, there's an invisible line here. There's an invisible line that the graph is getting close to but can't touch. So is it approaching that line from the top of the line or is it coming in from underneath? From the top. That's why if you ever see a little plus, that's what the plus means. But you won't see that. I haven't seen it. But if you do, that's what it means. Okay. Look at the second part, because how many arrows does a growth have? 2. So we asked about the left arrow. Now let's look at the right arrow. As x approaches positive infinity, if what direction are you headed if x is going to positive infinity? The right. So if I look at what the right arrow is doing on a growth, what's that doing? Yeah, and then that's going on forever. So on a growth, if you ever see any behavior as x goes to positive infinity, y also goes to positive infinity. What the heck does that say? Let's look at a decay. This other drawing over here. First, we start off at a condition. As x goes to negative infinity, what direction is x going if you're going to negative infinity? Kiara, what direction is x going if you're going to negative infinity on the x-axis? Give me a directional word. Martha, if the x-axis is, yeah, left. So on a decay, what's the left arrow doing? What is the left arrow doing on a decay? If you're going left, what other direction are you also going? You're going up. How far up are you going? Forever. That doesn't stop. Okay, that's going up forever. So you would say, as x approaches negative infinity, y approaches positive infinity. The second part says, well, how about when x is going to positive infinity? Positive infinity for x means the right. That's a way of asking, hey, by the way, what is the right arrow doing? Well, when we're going right on a decay, we're also going down, but how far down are we going? Huh? Only to the asymptote. It's never going to, it's going to like level off, and you're never going to reach the asymptote. Where's the asymptote going to be at? At k. If it looks like this and this asymptote is right around here horizontal, and you're coming at it from the top, you might again see that k plus. That little plus just means that you're coming from the top. That's all that means. If it was coming up from the bottom, because like think about it. If this were to flip, let's say a is negative, right? And this does an x-axis flip. Now the decay would look like that if it were to flip, if it were to be a variable. I would still have an asymptote, and it would still approach it, but where would it be coming at it from? From the top or from the bottom? From the bottom, it's underneath, so then you would put negative, k negative. But I don't think you're gonna see that. All right, we're gonna start some examples. And we'll do this for the next 2 days. Use the parent function of f of x is equal to 2 to the x to describe the transformations. It doesn't look like this is going to be too important here, but just so we get in the habit of it, if that is the parent function, what type of exponential function is this? Because there's 2 types of exponential functions. Which type would this one be? Even if you were to guess, it'd be a 50-50 guess because there's only 2 of them. Huh? This would be a growth. And just so, I mean, for these questions, it doesn't look like I'm going to need to know that, but how do you know it's a growth, Marquise? Because what? What is the 2? What did I call the 2? The base, yeah. And it's not that it's positive. It's that the base is what? Greater than 1. Any base that's greater than 1 is and then Nakai, I remember you kind of raised an eyebrow when I said this. Like, let's say that this would have said negative 2x. See how there's no parentheses? The base would still be 2. What that negative would count as is a. Because you can't have a negative base. There would be discontinuity. The graph would jump all over the place. Alrighty. So in order to be able to describe, it's a different type of graph, but this is the exact same thing we did on the last test. Everything revolves around identifying A, H, and K. For this first one, what's A? Oh, look at that, wow, the thing I was just talking about. Perfect. What's A there? Negative 1, yeah, A here is negative 1. That negative 2 is that you can't have a negative base. Let's take my word for it. It would jump all over the place. What's H going to be here? Remember, H would be the little number on the exponent. Huh? H would be 0. Nothing is being added or subtracted up on the exponent with the x. And what is K? 3. If I were to go up to you a week ago and say, hey, I have some function, who cares what it is? A is negative 1, H is 0, and K is 3. What type of transformations are occurring? You could have answered this already. It's the same thing as with the only thing is instead of flipping a U, we're going to be flipping a different type of shape. That's the only difference. And translating, but it's the same transformations. So can somebody tell me what these transformations are? What is occurring here? Let's describe the transformations. We have an x-axis reflection. How do you know that we have an x-axis reflection? Because A is negative. Good. Do we have a stretch or compress? No, because the A is 1. Do we have any other transformations? It's going where? Good. K is 3, so vertical. I don't have that much space. Vertical translation of 3. Nakai, not a vertical stretch of 3. Vertical translation of 3. Fair warning. You know how we have all these common assessments, and I showed you for the last test the key that I was sent and stuff like that, and I try to grade you along the same line as any other teacher would grade other students. So on that test for the translations, they didn't require the students to write in vertical. The word vertical, I guess, was implied by up. Like you had to at least say up. But if you didn't use the word vertical, I didn't take away credit from you because it doesn't look like anybody else did. Still vertical, but the other teachers didn't take away credit. So, whatever, bro. All right, how about number 2? Kiara, You give me A, H, and K. Let's go. Here's an easy one. What's A here? 4 is a number in front. Good. What's H? Huh? What is H? 4. I mean, you gotta change the sign. Yes, you are correct. There's a -4 there, but you gotta change the sign. What's K? H is K is 0. Sorry. So let's name that transformation. Caleb, you're having a slack day today, man. Let's pick it up. Tell me what transformations are going on there. Good. Vertical stretch by a factor of 4. Sometimes people put vertical stretch times 4. That's fine. A little extra times. Any other transformations? Good. Translate. Right. For you. What? Times 4. Sometimes when people say, like, before I would write by a factor of 4, a lot of times when there's a stretch, people just put times 4. It's a magnitude. It's saying how much you're stretching by. That's just the x's. And in that case, I'm not writing it as a variable. I'm writing it as like multiplication. Here, watch. I'll make it better for you. How about that? How about if I just say of 4? If that's confusing to you. Of 4. Oh, that's an ugly of, Marvin. Marvin, you do the next one for me. It's A. So this is a little trickier. It's going to require the use of all of your senses. What's A here? Huh? No. A? No. I'm going to pass it off to Nakai. Go on, Nakai. What? Martha. What's A on number 3? You think Shelby knows, don't you? No! And A is -2 over 3. What is H? 0. What is K? Also 0. So what transformaciones are happening on 3? Yes, we do have an x-axis reflection. How do you know that, Marquise? A is negative. Yep. Anything else? Very good. You can have a vertical compress of how much? Of how much? Yeah, of 2/3. Good. The only thing different here is where you find A, H, and K. Because once you find them, I bet I can jump in my time machine and go back a week ago and ask you the same questions, and you should be able to answer them. The only thing different today is where do you find them? Brandon's going to help us out and find the next one. That's what Brandon does. He's a problem solver. Give me A, Brandon. Now! No! We already did one like this before. And Kiara, we trust. Yes, good. -1. And H. Thank you, Jada. And K. Shobi, give me some transformations. I don't want to. No, nothing? Ingrid? I'll pass. Jason, J Money, give me a transformation. That's what's happening there. Good. How do you know that there's an x-axis reflection? Because A is negative. So like we already talked about how this was a growth, right? And growths typically look like this. So if I were to graph this, it looks like I'm still have one more transformation left, but before I do that transformation, this would end up flipping and end up looking like that. And what's that last transformation? Yeah, translate down 5 units. 5 unidades. Did you sleep in that last night? Did you sleep in that last night? Because it looks like you're wearing your PJs with your Trae Young jersey. Who's their sponsor? What does it say on the top there? Share Care? All right, Nakai. Let's go. Show us how you do it on the court here. Number 5, what's A? Half. What's H? Good, -3, good. And what's K? Excellent. Sam, I am. What transformations are going on there? Good. Wow. All right. Vertical compress of how much? Good. Vertical compress of 1/2. And anything else? Translate left 3. Horizontal translation left 3. Bri. The last one here, number 6. Tell me the A, H, and K. What's A? It's the 3rd time this happens in this little group of problems. It's the 3rd time we've seen this A. Huh? -1. Good. What's H? N-O. Martha, you know? +1. Good. The little number here, you gotta change the sign. And then what's K? That one, sir. If you can't see the screen that well, you can take paper. So let's see. Jada, give me some transformations that are happening here. Show x-axis reflection. Huion, can you give me the other transformation there? Good, translate right one. Let's see. I think that, see, the only thing I can think of is that other teachers teach their kids to do this by substitution and like kind of like a guess and check, making a table. I'm gonna show you something a little bit different. Okay, let me see what you do with it. Look at number 7. What is the base? So, unlike like with quadratics, where I was able to give you, if you were with me last semester, I was able to give you a set of points to start with. Like if you remember 1, 1, 2, 4, 3, 9, 4, 16, and you could use any of those points. We would use 1, 1, and 2, 4 the most. I can't give you a set of points because the set of points is always going to change depending on the base. So what you're going to have to do first is come up with a set of starting points where you have to identify the base. Okay, so we're gonna have x and then 2 to the x. Here's my advice to you. This is not perfect advice. There's sometimes where it might not help. It's never gonna hurt you. It might not help you, but it's not gonna hurt you. My advice to you is if you have a growth, use positive x's. Also 0. 0 is actually the best number in the world to use. It's awesome for exponentials, but use positives. If you have a decay, use negatives. You can pick whichever one you want. You already saw in the last slide. Okay, what direction does x go? What direction does the x-axis go? Left and right. How far do all of these functions go left, and how far do they go right? Infinity. These things never, they are going to stop up and down, but they're not going to stop left and right. So you can pick whatever x's you want. What I recommend to you is for growths, use 0 and positives. For decays, use 0 and negatives. Let's go with 3 points. 3 points I think should be enough. I'll do 4 just to show off, but I think 3 points should be enough. What number did I say I want to start with? 0, yeah. 0 works great for these things. Is this a growth or a decay? So what numbers did I say to use? So let's do positives. 1, 2, and 3. I'm gonna do 4 points. Okay. So now the question is, let's take turns plugging this in for x. What is 2 to the 0? What is 2 to the 1? What is 2 squared? What is 2 to the 3rd? So think of these as ordered pairs. They're not going to go in our final graph, but these are the points we're going to transform. We're going to start off with these and transform these. In order to transform them, I need to identify A, H, and K. What's the A here? The A is -4, good. What's the H? 0, what's the K? You don't necessarily have to do this now, but if it helps you not to forget, because this is a critical part of the graph, it has to be there. All exponential functions have a horizontal asymptote. Where did I tell you the horizontal asymptote is always going to be at? At where? K. What's K here? 0. So I would find 0 on the y-axis. Yes, I said that correctly, on the y-axis. And draw a horizontal dashed line through there. My graph is either going to be entirely above this or entirely below it. Based on the fact that they're giving me most of the graph below it, I'm guessing it's going to be below. Can anybody look at the graph and tell me why they know it's going to be below the graph? What has occurred based on these transformations? Heck, what's one of there's only 2. What are one of the only 2 transformations here? Yeah, there's a reflection. It's flipped over the line. That's why. All right, so let's do this. Let's start off with 0, 1, 1, 2, 2, 4, and 3, 8. Where did I get these points from? From the table that I made. Okay. And let's use that formula that I gave you on the bottom of the first page. And once I use it, then I can graph those points. Okay, so the first x here is 0. What am I supposed to do with the x's? Plus h, but what does h also happen to be? 0. So 0 plus 0, comma. What's the first y? 1. Okay, the first y here is 1. Times a, what was a? -4. And then it's supposed to be plus k, but k is also 0. You don't really have to write this, but if I don't write it, you guys are gonna be like, oh, but what happened to H and K? I don't get it. What happened to H and K? I don't get it. Hold on, I'm trying to think of an easier way to do this. I'm gonna be on the graph. Yeah. Alright, I'm gonna do it this way. I'm just trying to think of this though. What's 0 plus 0? Comma, what's 1 times negative 4 plus 0? Negative 4. I can go ahead and put that point on the graph. 0, negative 4. I know that's going to be on the graph. Okay. Look at the next one. Let's start off. The first x is 1. What am I supposed to do with x's? Plus h. H happens to be 0. The first y is 2. 2 times negative 4. K is 0. So you don't even have to really write those plus zeros. I'm just writing it so you know it's there. 1 plus 0 is 1. 2 times negative 4 is negative 8. I can put the point 1, negative 8. 1, and be careful because it looks like with the x-axis, they're counting by ones, but then on the y-axis, they're counting by twos. They go. Actually, no, they're not. I take it back. No, they're not. They're still counting by ones. Take it back. Have I confused anybody yet? Here, I'm going to erase this because I'm running out of space. You have it on your paper. Let's do the next point. 2 comma 4. What's the x of that point? Now I'm doing this one here. What's the x there? What's the x there? 2. What am I supposed to do with that 2? I'm supposed to add 0, but adding 0 is not going to do anything. H is 0. It's not going to do anything. Okay? And then the y is 4. What happens to the y according to the formula? Times a, which is negative 4 plus k, but that's just 0. So we end up with 2 negative 16. 2 negative 16. Now I was going to do this fourth point, but I can tell if I do this fourth point, it's going to be 8 times negative 4, which is negative 32. It's not even going to fit here, so I'm not even going to bother with it. So now it's really just a sketch. You don't have to be perfect. There's no straight edge. It's not straight, but I need to connect the dots. And also keep in mind that as we get closer to this asymptote, it's going to get close, but it's never going to touch it. So if I were to try to sketch this, remember it's going to be kind of curvy. It would look something that. Let's try again. You cannot touch an asymptote. That's one of the things I would look for on a test to see, make sure that you don't touch. It's going to be getting closer and closer, but as it gets closer to the asymptote, it flattens out. Let's see if we can do one more before the bell. Have I confused anybody yet? Okay, first let's do a table. X, what is the base here? So 1/2, and because the base is 1/2, what type of a exponential function is this going to start off as? As a decay. To me, where this is the most important is it tells you what x is to pick. You can pick whatever x's you want, but to me, like that's what this that's what this helps you with. Kiara, what's the first x I told you should start with? Because it always works out the best. 0. The reason why 0 is because any number to the 0 power is always going to be 1. What did I tell you should pick after that? Negatives. Yeah, I would pick like -1, -2, and if I have enough space, I don't know if I'll have. Hey, let's say this one I should have enough space. -3. The reason why I picked negatives, remember, these are exponential functions. Yesterday we went over properties of exponents. When I plug in this -1, it's going into the exponent. What did we learn yesterday that negative exponents do? We did it yesterday. What do negative exponents do? They flip the base. Nobody said anything, but you're probably having a heart attack when you saw this fraction there. But what that negative is going to do is it's going to flip the base. So instead of the base being 1/2, what's the reciprocal of 1/2? 2. What is 1/2 to the -1 power? It's the same thing as saying 2 to the +1. What's 2 to the +1? 2. If you use that same logic, what's 1/2 to the -2 power? Same thing as saying 2 to the +2, which is 4. And then what's 1/2 to the -3 power? If you're somebody that's overly reliant on a calculator, the calculator will take care of you. If you put this into the calculator, it'll tell you what 1/2 to each of these powers is. So now I'm going to use these as my starting points. But I need to know what my transformations are. So let's identify A, H, and K. What's A here? -1. What is H here? Coincidentally also -1. And what's K? K is 0. The more experience you get with these, the more experience that we get with these, you'll know that if A is ever 1, +1, you can ignore it. If H is 0, you can ignore it. If K is 0, you can ignore it. It's not going to do anything. So which of those numbers can I ignore right now when I'm about to transform? I can ignore K. K is not going to do anything. I can ignore it. What points am I going to start at? The ones I got. 0, 1, -1, 2, -2, 4, and -3. And for the second time, how did I get these numbers? How did I get those numbers? From taking 1/2 to the power of those x's, and then I got the y. 1/2 to the 0 is 1. 1/2 to the -1 is 2. 1/2 to the -2 power is 4. 1/2 to the -3 power is 8. So now let's get these and transform them. The first x is 0. What do I do to the x's? And actually, hold on. Let's even do this. Where's the asymptote going to be at? Where is the asymptotal going to be at? Where's the asymptote going to be at? Yeah, it's going to be at 0 at K. But now that I know that, let's do the transformations. What am I supposed to do with the x? Add H. What's H here? -1. What am I supposed to do with the y's? Times A, but plus K. But I told you we can ignore K, so let's just do times A. So what is 0 minus 1? -1. What's 1 times -1? Also -1. So I can put the point -1, -1 on my graph already. For the next one, my x is -1. What do I do with the x's? According to the formula, what do I do with the x's? Add H. H was -1, so -1 minus 1, comma. The y is 2. You're supposed to multiply times A, so times -1. -1 times -1 is +1. 2 times -1 is -2. I can put that point there also, 1, -2. For the third time in a row, what am I supposed to do with the x's? For the x's, I'm supposed to add H. So -2 is the x here. Adding H is the same as -1. Then I have a 4 times the A. So I get 2, comma, -4. I can put a point there, 2, -4. Since this one didn't get stretched out like the last one, I can actually fit an extra point here, which gives me some more definition on my graph. The x's, you add H, so -3 minus 1. And then the y is times A, So 8 times -1 gives you a -4, -8. So -4, -8. Did I go backwards? Did I mess this up? Hold on. I just gotta fix the x's. -1 minus 1 is -2. -2, I did multiply, sorry. -2 minus 1 is -3. So let's just, hold on. -2 is there. -3, -4 is here. And then -4, -8 is there. Draw the lines, but remember to respect the asymptote. Did I confuse anybody? Sorry, I messed up these subtractions. Just make sure that you fix these. The subtraction there. I messed up in my handwriting. I did multiply. And did I confuse you? Tomorrow we'll continue. Make sure you bring this back tomorrow. Are you writing your system note? Tomorrow we'll try to finish as much of the last pages.